All right. Well, we're very excited today to welcome you to our webinar featuring Jeff Webb. My name is Joy Koo, and I'm one of the executive committee members of the Committee on Credible Practice of Modeling and Simulation in Healthcare, and I'll be serving as the moderator for the webinar today. Very pleased to welcome today's presenter, Jeff Webb from Applied Research Associates. Next slide, please. The Committee on Credible Practice of Modeling and Simulation in Healthcare, or CPMS, is an initiative started by a consortium of the U.S. funding agencies called the Interagency Modeling and Analysis Group, or IMAG, and also the Multiscale Modeling Consortium, MSM. Our goal is to establish guidelines for simulation-based medicine so as to increase the adoption of modeling and simulations within clinics and healthcare in general. Next slide, please. The key goal of our webinar series is to showcase how individuals have translated their modeling and simulation research into clinical use, and also to engage the community in discussions on best practices for modeling and simulation. Next slide, please. So before we get started and get to the good stuff, I have a few reminders about the webinar format. First of all, questions are going to be addressed at the end of the presentation via the text-based Q&A panel. Our presenter will verbally answer these questions at the end of his talk. And we also have other members of the BioGears team who will be answering questions via text throughout the talk. So if you have any questions, you can go ahead and put them into the Q&A panel during the presentation. And if you need additional technical help, you can also consult the guide that's on our website. Next slide, please. And now I'd like to introduce Jeff Webb. Mr. Webb is a senior engineer at Applied Research Associates. He has experience in a wide range of research and development, product development, data analysis, and program management tasks. He has extensive experience working with software, hardware, and sensor interfaces for several different programs. Mr. Webb is currently the BioGears project principal investigator, and he's responsible for contract performance and ensuring the successful integration of physiology modeling methodology into an advanced software design. So this includes the coordination of several engineers and software developers to deliver a fully functional lumped parameter-based engine with a common data model and anatomical database. So Jeff, we look forward to hearing your presentation.
Thank you very much, Joy. Good afternoon, everyone here on the East Coast, and I guess good morning for everyone with Joy on the West Coast, and good evening just to cover all my bases because I saw people who are international registered. And I'd also like to thank the committee for inviting me to speak today. I think what you guys are doing is great, and I think this is a really good opportunity. Today I'll describe a little bit about the focus and goals of the program itself. I'm not going to get into too much technical detail. I originally planned to talk a lot more about kind of how we do the modeling at a low level, but Joy kind of steered me the other way, so it'll be a little more anecdotal and a little less boring, I hope. So, this presentation should go relatively quick. I don't have a ton of slides, and hopefully we'll have a lot of time at the end for questions. A little bit about just the program background, just the programmatics that I'm kind of required to say is, you know, the organization I work for is Applied Research Associates. We're funded through TATRIC. You can see the award number there. And the amount is about $7 million, and our period of performance started back in 2013, and we still have about another year left on this bolus of funding. And the disclaimer there is obviously I do not work for the government, I do not speak for the government, so these opinions are only mine. So just a little bit about some of the high-level objectives of what the program is and what we're trying to achieve, and why our customer decided that it was something that was needed. Basically, they wanted to create a publicly available physiology platform. I've been told that they were getting sick of spending money over and over again to pretty much reinvent the physiology wheel. And they decided that if they just created an open source available engine, then they could actually save money in the long run, and you could get community involvement, and everyone could add their own models, and it would be a great starting point and platform for anyone else who wants to do any sort of modeling and simulation work with the human body. So in that way, they wanted to lower the barrier and engage the community to, of course, meet the training needs of the military, since this is being funded by the military. Also, beyond that, we just want to expand the body of knowledge of kind of what's out there and kind of use some novel approaches and some good models and use a modular and extensible approach to implement everything. So to kind of describe what BioGears is, sometimes it's even easier to describe almost what it's not. So BioGears is a powerful backbone for applications. It's not a game itself. It's not an application itself. It's something you can build your fancy applications on top of. So it powers the immersive training content. It's used for other modeling and simulation tools. We've included a lot of different tools that are very leverageable for any number of different applications. And we focused on patient variability using homeostasis with different conditions, insults, and interventions for pathophysiology, which is a little bit different approach than other people have taken, I'll talk about in a little bit. So the way I kind of like to think about it is, BioGears, we do call it an engine. It's a software engine. So it's kind of similar to if you bought a car frame, engine, transmission, and all you needed to do at that point is add, fancy interior, maybe some fancy rims and a paint job. And it's way cheaper and easier and a better starting point than just working from scratch. And you can use it for not only applications, directly through our programming interface, but you can also use it for a lot of different other research applications by getting in there and modeling some of your own work and doing some hypotheses. And I'll talk more about that later. Another thing that you can do in that last bullet there is, in the future, we would like to be able to directly ingest patient records, and you could even create almost like a personalized avatar of either you or someone you know, and then that'd be a good way to kind of do predictive modeling. So I'll describe the team who's working on this. It's a nice eclectic mix of people, which I think makes a better product in the long run. If you see me as a PI up there, then we have Jen Carter as the program manager. She's also in charge of the community outreach. She planned our BioGears conference that we had, and she oversees anything with website, anything else that a PM would normally do. For physiology modeling, Rodney Matoyer is our in-house clinician. He is a former combat medic. He's also a mechanical and aerospace engineer. So that's a good kind of mix of skills that really help us when we're putting models and making sure that they make sense clinically. Austin Bird is a PhD with applied math. He did a lot of modeling of renal system when he was in grad school. And so he gives us that good low-level kind of math, make sure we're doing things fast and correctly and everything's conserved. Bennett Welsh is pretty new to the team. He has a background in biomedical engineering from school. He's also done a lot of work with software development and programming. So we're getting him spun up on all the different unit tests we do to make sure that everything's working properly. And then for software architecture, Aaron Bray is our lead there, and he's put together our common data model and made sure that all of us engineers do things appropriately within the software, because a lot of times we get lazy and it wouldn't be nearly as usable. And then David Bird helps a lot with deploying it onto multiple systems. So we not only deploy to Windows, but also Macs, and we're on Linux systems as well. And then Tony Hamilton is our website developer. I think we have a pretty fantastic website. If you go to biogearsengine.com, you can see his work there. And so we lean on him anytime we want to make any changes or additions to the website. And then beyond just our team here at ARA, we also have a lot of subject matter experts. So Brian Bergeron, sometimes it's actually easier to say what he doesn't do rather than what he does do. He's a consultant, author, educator. He's the editor of Servo Magazine. He's written several books. So he helps us a lot with validating our models. Dr. Nick Moss is a physiology professor for many years, and he's been described by some of the team members as basically a human encyclopedia of physiology knowledge. And then Stephen Mangum is our in-house pharmacist, and so he's a pharmacy SME, and he helps us with all of our drug modeling, our pharmacokinetics, pharmacodynamics. And then you can see on our government side, the JPC1 director, Joint Program Committee 1 is Jan Harris. The portfolio manager is Kevin Kunkler. And then Harvey McGee is our grants officer representative at TATRIC, which is the Telemedicine and Advanced Technology Research Center up at Fort Detrick. And then Jeff Miller is the research scientist, basically chief scientist that we interface with on this program as well. And then you can see listed some past contributors. Moving on, just to give you an idea of where we are timeline-wise, we started back in 2013 with the project kickoff. We had a mini build release, basically our alpha build a year later. And then a year after that, in October of 2015, we had our beta build release that coincided with a users conference. I'll talk a little bit more about that. What we're working on right now is transitioning from a beta phase to our first release candidate. So we're hoping to get that out sometime in the next month or two. And it'll be a lot, better version of the code than what's out there now. And one thing I would love to add to this timeline at some point is at the end of it get some sort of accreditation through the CPMS program. So that would be definitely a helpful thing to add. So now I'll talk a little bit about how we built our user base and who's using our models and how we kind of talk them into it. So the first group is the easiest way to get people to use it is when the government pays you to do it. So here are some of the government programs that have used either BioGears itself or precursors of BioGears. So you have the Advanced Modular Mannequin Team, which is being funded through MRMC, and that's kind of a similar idea to BioGears software-wise, but for also hardware and making sure you have interchangeable parts with mannequins. RDECOM funded Combat Medic, which was a serious game that used an early version of BioGears to train on the preventable causes of death on the battlefield. Human Simulation Airway was another program funded by TATRIC that used an older version of BioGears. There's also BioGears has been showing up in a lot of requests for information and a lot of small business initiatives, a lot of requests for proposals. And so I've listed a few of those there. So it's starting to gain steam, and of course the government's keen on using it since they're the ones funding it. So that's really an easy way to get users is to basically be forced to do it. But more exciting are some of the other known integrators that we have. I've separated these sort of into categories. You can see there and talk about some of the advantages they offer. So you can use it for simulation systems for things like serious games. Virtual Heroes is using it, VCOM3D is using that capacity. It's an easy way to do a patient variability, and you can do games working on patient management, and you can leverage our existing library of conditions and salt interventions. And this could be used for either virtual reality or augmented reality as well. Some of the hardware integrators, a lot of them go along with that Advanced Modular Mannequin program. You can see those listed there. It's BioGears is low size, weight, and power. It's meant to run on a standard PC, just a low-level laptop, faster than real time. And it's just an easy way that you don't have to start from scratch if you're trying to create a mannequin for training applications. There's also uses with task trainers. I know Ingmar Medical they're known for creating respiratory task trainers, and they're using it in various ways. Some of these I don't want to go into too much detail because we have non-disclosure agreements, and I'm a little concerned that if I talk about kind of the details of how they're integrating it, that maybe that isn't exactly what the users would want. But then also we have researchers and educators. So Kitware recently wrote a paper that was using BioGears as a research tool to determine the best way of performing surgeries. And then you can see some other universities that are using it in the classroom as a teaching tool. We also have, contributors. So ARA, of course, is a contributor. We've worked with the University of North Carolina in their pharmacy school for our initial design of our pharmacokinetic and pharmacodynamic model. And then Brian Bergeron, who owns his own company, he's one of the subject matter experts on the program that I talked about earlier. So one way that we're actually right now looking for some contributors. So we've had over 3,400 downloads of the software, but we're still looking for our first upload. Obviously, since it's still a beta version and it's only been out for a year or two, it's still kind of early in the program. But if anyone would like to make additions or add models, we'd love to hear from you, and we'd love to add them to the library of the models that we use. Now I'll talk a little bit about kind of the implementation and the way that we deployed it. So first, just a little background on the modeling approach, where we started, why we do the modeling approach that we do. So it started way back in the 60s. So if anyone is familiar with Guyton, he actually is kind of like a god of physiology. So Guyton and Hall is the textbook of medical physiology that a lot of students use as they go through their programs for biomedical engineering. And there's a doctor named Dr. Ty Smith, who is a contemporary of his, and he has numerous publications. You can go see those on PubMed. And throughout the 90s to the mid-2000s, he worked with a man named Ken Starko, who actually came from the aerospace industry and did software development for flight simulation, and they developed a model called body.dll. That model was eventually purchased by my company, ARA, in the 2000s from their company. And basically, we've been advancing it ever since then, and it was a good starting point for BioGears, so we kept that same approach. You can see on the right there a simple 3-element Wim Kessel, which at the lowest level is kind of the style of modeling that we use. It's loosely translated from German to English to mean air chamber, but it's basically generally taken to imply an elastic reservoir. So that's a kind of a typical way of modeling whole body physiology and breaking it down kind of a high level. You can see also below that the crazy circuit diagram that Guyton used way back in 1972 to try to simulate pressure. So you can see how this type of modeling can vary fidelity up and down pretty easily. One thing that's kind of funny, though, is I would guess at this point there's not a single line of code that actually still exists from that original model that we started with back in 2013. We've probably replaced it all with what I consider better versions, and so you could kind of look at our history through software development, kind of see how we replace those kind of piece by piece throughout. So a little bit about kind of the fidelity and why we chose the fidelity that we did for all of our different models. So some of the things that I talked about were key. We have to be faster than real time, so that takes out a lot of the slower models, like doing any sort of computational fluid dynamics, whether it's 1D or 3D. It's probably not going to be able to run fast enough for a whole body simulation. State-based models are more cause and effect. They're not necessarily what we want for this, because it's hard to stack different insults and conditions and do different actions at the same time. So we decided to basically go with a 0D physics-based model. And not only was that our starting point, but after we analyzed if there's other ways to do the modeling approach, we decided that was the best option. Fidelity for a whole body physiology is actually a little bit different than people normally think in the realm of biology. Since we're talking about whole body physiology, generally low fidelity is more time or state based. There's little to no actual physiology. A lot of the death is based on predetermined number of wounds or time after a wound without intervention. Many people are probably familiar with the Office of Naval Research, ONR, MCIS codes. That's kind of a way to take, there was an explosion, there's a severity of a wound, well, let's determine if he died or not. There's no actual physiology going on in the background. Medium fidelity for physiology a lot of times is more semi-autonomous physiology based on the actual algorithms, but it's normally scenario driven and everything's predetermined by the author, so it's not quite as dynamic as what we're looking for. Whereas what would be considered high fidelity for full body physiology is self-compensating models based on human physiology and systems interactions, and it's a lot of times outcome based on the intervention itself. So we've instituted, that what's considered a high fidelity whole body physiology model with pretty complex interactions that I'll get into a little bit later. And so obviously all these different approaches have different trade-offs, speed, accuracy, modularity, extensibility, fidelity, scale, complexity. So it was really tough for us to try to determine where that right balance is. And so where we determine that right balance is kind of what I call the Goldilocks of fidelity. So not too high, not too low, just right. So we kind of did a middle out approach because we want to allow these models to not only run fast enough to do whole body physiology, but allow people to kind of use them for research programs as boundary conditions and to be able to extend it to different models that they would want to do. So BioGears is an integrated organism-level human physiology simulation engine. It's built from systems, organs, and tissue level computational models. So some of the key decisions we had when we do our modeling is we want to do mechanistic modeling wherever we can possibly do it. If we can't figure out a good way to do that, or maybe it's unknown, we've been back out of that to phenomenological models otherwise. An example of where we've used more of a phenomenological model is for our pharmacodynamic modeling approach, which takes the concentrations of the drug in the tissues and determines what the change in things like respiration rate, heart rate, just does it based on that concentration. A little different than most of the mechanistic models you would normally see with some higher fidelity PK/PD modeling. Another thing that we focus on is precision and accuracy, and also rigor and reproducibility. I mean, those are obviously keys for any models that you're going to create. One thing that is tough when you're doing this type of modeling is to understand that correlation does not always mean causation. So we use our correlation for validation purposes, but the causation is really the implementation, that feedback mechanism we use. An example that I like is with the tubuloglomerular feedback that we use with the renal system, where the kidney regulates the glomerular filtration rate based on, mean arterial pressure changes. A lot of other models are actually based on the pressure itself. So as that pressure changes, it just automatically changes the glomerular filtration rate. Or our model is more like the human body's actual processes, where it looks at the sodium delivery and then it changes the afferent resistance, which then leads to a glomerular filtration rate change. Now, even though we implemented it using that feedback mechanism, we can still use the mean arterial pressure to do the validation, because that's a lot easier way to see if the response is doing exactly what you want. And then so we have to make sure that we balance fidelity appropriately. It wouldn't do any good to have a much higher renal system than cardiovascular system, for example. And then one note I have here is that I feel like after doing this, it seems like the way that we go about modeling is equal parts biology, math, science, and engineering, but also almost black arts. Like after you keep integrating models over and over again and get used to doing this type of modeling approach, it almost becomes intuitive how to select models. But I'll talk a little more about kind of breaking down how we do the model selection process. So we're a little unique in that we're both a consumer and a creator of models. So what we typically do is look for usually peer-reviewed existing models that hopefully are derived from empirical data and that use a sound physics approach. So we have to make sure that we do conservation, because as we do this whole body approach and we do the feedback mechanisms, if you start losing energy or mass anywhere, it's going to kind of screw up all your systems in the homeostasis of those systems. And so when we can't find exactly what we want there, or if it just doesn't fill all the gaps, then we start filling those gaps in with some of our own models. And a lot of times we look at textbook or other published papers as starting points for those. And then one way that we do that is by employing a methodical design review approach. So we actually go from a preliminary design review, where we normally just have a high level, what does this system do? What do we want it to do? What are the requirements for the system? What is the existing documentation? Then we get into what we call an intermediate design review, where it's, okay, now how are we specifically going to model that inside of BioGears? And then when everything's done, we have a final design review, which is basically a code review, and we look at the validation and make sure that everything is the way we want it. And so some examples of how we've chosen those models, you can see from that first bullet, is some of them we've inherited. So the modeling, the actual body.dll software that we started with, that I talked about in the beginning, we actually inherited that style of modeling the cardiovascular system, and we've just advanced it from there. Some of the systems we've extended from existing, and I'll show an example of that later, where we've taken the cardiovascular system, which had that 3-element Wynn-Kessel model for the renal system, and we've expanded that to a much higher fidelity model. Some are derived from external sources. So an example of that is our drugs, or our pharmacokinetic and pharmacodynamic model. So there's actually, when we worked with the University of North Carolina Pharmacy School, They already had some existing software to model in a similar fashion to what we want, so we kind of ported that over to our C++ version of the software. Some are a combination of external sources. The environment is a good example of this. At least for the thermal side of things, the environment system that we've modeled, we leveraged the American Society of Heating, Refrigeration, and Air Conditioning Engineers Handbook, and specifically their chapter on thermal comfort for a lot of the equations we use there. And then also there's an ISO standard, 7730, that does similar things. One of the problems that we found with that ISO standard, though, is we found software for it, but it doesn't go outside of normal bounds. This is mainly for indoor environments, and obviously when we're testing, if you're going to use it for a combat medic training, you're going to want to have it in outdoor environments in some extreme conditions, high altitude, even submerged. So we had to extend the model for that. I also noticed that it didn't conserve energy completely. Our model does conserve energy, so it's kind of too hand-wavy, in my opinion, for what we're trying to do. So we took a lot of the equations, integrated them in, but then added our own. A lot of our other models are developed from scratch. The energy model, I'm sure, it's a lot of the equations are based from documentation, but a lot of what we do with our exercise model was kind of created in-house. Some of them are re-implemented fresh. So the anti-fusion machine, we did have a model for that as a starting point, but it was not, I guess, up to what we wanted. So I went through and completely rewrote it, and it was a lot faster and easier to actually create one from scratch than it was to try to fix an existing model at that point. And then some of them kind of warehouse information, like the blood chemistry model is basically just looks at the cardiovascular system and tries to see what substance concentration values and other information are within that system. Another great example of how we do our modeling approach is what we're working on right now for our acid-base balance model. So we looked at some of the more well-known models like the Henderson-Hasselbalch equation, which is kind of a first principles relationship of bicarbonate, CO2, pH, but it ignores a lot of the other things that we care about. We also had the Kelman equation that everyone knows for the dissociation curve for binding O2 and CO2 to hemoglobin. So the model, if you download the software right now, uses those two approaches, but it wasn't really doing everything that we wanted. There were lots of problems with crashes, so we decided that we wanted to redesign it. So throughout research, we decided to reject the Copenhagen and Boston models, which is more just to kind of describe the outcomes of what's going to happen with alkalosis, acidosis, things like that. And we went more for the Stewart model, which if people are familiar with that, it's a full physicochemical model derived, and it describes all the mechanisms that are involved, not just kind of the outcomes. So it's a lot more the way that we want to model things. And so we also kind of combined that with the dash Bassing weight approach for O2 and CO2 binding, and we do it simultaneously with pH. And then we have an iterative solution to satisfy all the equations. And so now we have a mechanistic approach that's based on the local values, and when used in combination with our transport and our production, consumption, and alveolar exchange, it gives you, the results that we're looking for and make sure that everything stays in homeostasis. And I'm sure I've oversimplified that significantly. If anyone has questions about that model, they can talk to Rodney Matoyer, who's one of our team members working on that. And I know he should be answering questions right now as I speak. Or feel free to email us or call us at any time. All right, so moving on, I kind of stole this 10 not so simple rules for credibility from a presentation that Ahmet Erdemir, who is a CPMS team member, gave at the EMBC conference just about a month ago. So I really like these guidelines. As I looked into them more, I kind of found that we were almost unwittingly following them. So we were trying to do, a good approach to make sure that everything that we were doing was credible and unknowingly followed these. So if I just run through them very quickly and kind of what we did to find the context clearly. So we do a lot of the needs and requirements, specifications, analysis. So we try to do that as well as we can. For us, it's a little easier than some other models possibly because we actually are contractually required to model specific things. For Rule 2, using the appropriate data. So and then making sure that, you know, it's relevant to our activities and that it can be traced back to the source. If you go onto our website, biogearsengine.com, you can go to the documentation and everything is referenced. You can click on that reference, it takes you to a bibliography, and it shows you exactly where we got all of our validation values, where we got all of our different modeling approaches, where we got any, you know, data that we use. And so we've kind of focused a lot on the documentation of things like that. For Rule 3, evaluating within context, we've done a lot of validation and verification, and I'll have a slide on that next. Rule 4 is listing limitations explicitly. So we definitely not only present the known issues on the documentation homepage, but each system in the methodology reports actually have their own assumptions and limitations section. So that's how we've tried to address that. Rule 5 is using version control. We use Bitbucket, which is a web-based hosting service for Git. We also deploy on GitHub, and we include our entire source code and documentation as part of that. So, you know, version control is definitely really important when you're doing any sort of software development like this. Rule 6 is to document things adequately. You can go to our website. I think that will speak for itself. We've tried to document things as well as we could with not only methodology reports, but also all the different software components, installation instructions, user instructions, architecture design, different tutorials. Then Rule 7, disseminate broadly. I mean, it's open source. We try to get as many people to use it as possible. It's one of the reasons why I'm even talking here today. So we definitely focus on Rule 7 as part of this program. Rule 8 is get independent reviews. That's one place that's actually a little bit tougher. You know, with our user base, they continuously provide reviews and tell us what they like and don't like, but we haven't really had any, and we also have some official programmatic reviews as part of the Joint Program Committee review process that they do annually. So those are good to make sure we keep everything in check and we're meeting the requirements. Rule 9, test competing implementations. This one is actually kind of tough for us. So, you know, I went through how we actually look at different models and try to test them, but we haven't really looked very detailed at a lot of the other physiology engines that are out there because most of them are proprietary and not open source. And you know, not only would it probably be technically illegal to try to go in and use some of their software, their approaches a lot of times use more state-based than mechanistic the way that we do it. So everything for us has to be compatible with our Apache 2.0 license. And that's a very permissible license, even more than the BSD3 license, which is one of the other ones we looked into. Rule 10, conform to standards. So we've tried to adopt and promote, you know, good operating procedures and guidelines. And I talked about kind of the way that we do our development process and review process and our coding standards. And we try to make it as repeatable as possible. So for us, I know the biggest challenges are definitely Rule 1, defining the context appropriately. Rule 9, like I mentioned, is a little tough because you know, there's not a lot of open source things out there. And then the 10th rule, conforming to the standards, it's kind of hard to determine exactly what they are. The only other entity I know of that's trying to even determine rules is the ASME, Verification, Validation, and Computational Modeling of Medical Devices, or known as VNV40, and that's a little more on the device side of things and not quite applicable for our code. So a little bit about the keys to success. Run through this pretty quick. So the biggest key to success is, I mean, you've got to have a solid software architecture. People are going to use your code. It's got to be easy to use. It's got to be understandable. So we've done this in different levels, basically, with our common data model, which is how we just define the interfaces, our application programming interface, which is how you can talk directly to the engine without even really understanding what's going on under the hood, and then our software development kit gives you examples of how to use the API for any of your other applications. So in the sake of time, I'll move on to modularity and extensibility. So these are things that are very, very important for this program, is to make sure that other people can use it for any number of applications. And I have an example here of increasing the fidelity from the cardiovascular system. You can see the way that we modeled the kidneys on the bottom left is just a 3-element Wynn-Kessel model. And we've now expanded that to this, you know, much higher fidelity renal system where we can do that glomerular feedback that I was talking about. changing that afferent resistance based on sodium delivery, among other things, to try to make sure we meet the requirements. So you could do that in any location in the system. If you had a model that you wanted to model the right arm with higher fidelity for whatever reason, you could also just add new nodes and paths and elements and do that pretty easily. The other thing that it also supports, and this is just a conceptual diagram, we haven't done anything to this kind of level, is you could use it almost as a way to, with boundary conditions and in series with some higher fidelity models. You'll no longer be faster than real time. It probably wouldn't at that point be used for training applications, but you could use it for different research applications, and you could use some of the existing tools within BioGears to see what happens to that model as you perturb different things in the system and have different patient parameters and salt interventions and other, anything else you can modify in the engine. So then moving on to our, what I call, credible approach, because this is the credible practice of modeling simulation in healthcare. We wanted to make sure that we were doing the appropriate things and everything was correct on multiple levels of our code. So I broke that down basically into these 5 different levels. And so the data model is the first level, and so that's just making sure we have a lot of different tests that determine the inputs and outputs are correct, that we do unit conversions. So we have a really cool tool inside of the code that automatically does conversions. You just set it to a value and get it to a value. So I know as an engineer, when I first started working on this, it was super frustrating that the cardiovascular system does all of the pressures in millimeters of mercury, the respiratory system does it in centimeters of water, the energy system does it in pascals. And so we don't have to even think about that. We know, because we've tested the unit conversion software, that we can just set and get values however we want. It also does compartment hierarchy tests to make sure that parent-child relationships work appropriately. And then we have other tests to make sure this 32-bit, 64-bit works for our GCC-compliant code for Windows, Mac, and Linux, because every time we deploy, it's a headache to make sure that it compiles on all 3 of those systems. So some of the utilities that we use, we also have data probes, which is just a way that you can, while running, output whatever data you want that's inside the system. You don't have to necessarily go through the API. Then the next level of things that we look at are what we call solvers. So there's the circuit solver, which actually solves the system of equations for that fluid circuit that I showed earlier for the cardiovascular system and other systems. It solves that automatically for you, so you don't have to worry about anything other than just modifying the elements through feedback mechanisms. We also do thermal circuits for the energy and environment systems, and then it has the functionality to do electrical systems, but we currently don't use that at this point. Then we also have substance transport for both liquid and gases, so it does it not only for the respiratory system, but also for the cardiovascular, renal, all the other liquid systems. And it automatically moves things based on the flow, kind of bulk exchange at that point. We also have blood gas distribution, which is what I was talking about with those equations, calculating the saturation, mass, and base balance, and then compartment balancing equations for that child-parent relationship, and making sure that if you modify the concentration on one compartment, then it'll go through and update the masses based on the volume with that concentration that you set. So there's a lot of really helpful tools that we've included to make creating new models quick and easy, and also to make sure that it eliminates locations for potential error. And so the way we test those is through unit tests. So each of these little areas, we have a whole bunch of different tests that you can go online and look at to make sure that we're getting the results we expect. We also test mechanisms. So each system has different mechanisms for their feedback, and there's chemoreceptors, baroreceptors, making sure different patient parameters change things within the system as we would expect. A lot of this is done by comparing with experimental data, and we create plots you can see in our methodology reports. And then for each system individually, we check to make sure that the homeostatic values are correct. We have giant tables where we look at all of these for the standard patient. We also make sure via the scenario driver that every single one of our actions, which is an insult or intervention, and each condition gives the outputs that we would expect, and we have entire matrices showing the outputs of those. And then after we do all the different individual bits and pieces of the code, we look at whole body physiology, which is actually probably the hardest one to validate and make sure is giving the results we want. It includes patient variability and some of the combined effects, and we run the software development kit, and we also run 4 of our showcase scenarios and look at the outputs with those. This is where we lean on our subject matter experts the most, because it's a little harder to say what's going to happen when you include, you know, a hemorrhage with morphine, and I have a tension pneumothorax, and maybe I've been exercising, than it is just say, you know, oh, I have a hemorrhage, so what are the results there? That the individual actions are really easy, not really easy, but they're easier to validate than the combined effects and what you'd expect there. So, but if we model things appropriately using, you know, sound physics and using those mechanistic approaches I mentioned, you should be able to stack things in any way you want and get results that would be similar to you would get with the actual human. So then I'm not going to spend a lot of time on this slide, but this is basically just showing our verification, validation, and all the crazy amounts of results we look at. And you can see that our approach generally, we say if we're within 10% of the expected value, we'll say that's a pass and we did a good job. If it's within 10 to 30%, it's not exactly what we wanted. And if it's above 30%, it's definitely not good. You can see one of the worst ones right now is the respiratory system. And it's kind of interesting, that one's specifically bad because our pneumothorax model was not doing what it should. We actually realized that even though in a lot of literature it talks about a shift in the mediastinum that would then cause effects to the cardiovascular system, that doesn't actually occur in humans. The reason that a lot of literature says that is because they test it with dogs, and dogs have different physiology, and that does happen in dogs, but does not happen in humans. So we've corrected that in the next deployment. We'll have that modeled appropriately. Another thing that we focus a lot on is community outreach. So we've done many publications, presentations, seminars. We have forums online, so you can post questions that we'll answer. You can have discussions. People can interact with each other. You can also get alerts if there's any news about the program. It's extremely beneficial to use standard terms we found. So instead of you know, some of the other models that we've seen for drug modeling, for pharmacokinetic, pharmacodynamic modeling, do things like they talk about a change in the resistance that would lead to a change in the mean arterial pressure, whereas we define our substances with physicochemical properties, so things that any pharmacist could look up in a book and implement, and in that way it's a lot easier to understand not only what's going on, but to add new things in the future. We also focus on standard outputs, like we have assessments that would give data in a format that clinicians used to seeing. We also output vitals as if you were watching a vitals monitor, the same values that you would expect there. And then we have compartment data. So we've done that, designed in a way that you don't need to understand the nodes and the paths and what's going on under the hood. You just need to understand basic anatomy to be able to get values out of the engine that you're looking for. Some of the things we found that our users care about the most, with clinicians specifically, they don't necessarily care about what's going on under the hood at all. They just want to make sure that the results are exactly what they expect when you have, you know, acute or chronic conditions. Whereas most researchers and educators care immensely about what goes on under the hood. And so it's kind of hard for us sometimes to balance those two. So we you know, can't hide anything or kind of wave our hand at anything. We have to make sure we model it appropriately so that both sides are happy. And then one thing that's really helpful from our community is it helps us kind of shift focus and reorder our tasks to make sure we're meeting their needs properly. That's one of the reasons that we rushed so quickly to get an alpha build out, is so that we could start getting feedback as soon as possible and start kind of determining what it is that the community needs to keep going. And so some of the future needs that we have determined with that interaction with the community is what we call serialization, which is ways to save states in the middle of a run. So whether it's after you initialize a patient or you know, after you've done a specific action, you can save it off and then you can load it up and it'll load from that same point every single time. That's something we're actually working on right now as part of the current program, and it should be out in our next deployment. Some things that aren't part of the current program, though, is a vitals override. So we kind of We kind of pushed back against this one for a while. A lot of mannequin builders would like to be able to say, you know, I don't care what's causing it. I just want the mean arterial pressure to be this specific value, or the heart rate to be this specific value, or the tidal volume, or any of the, you know, typical vitals that you would see on a monitor. They want to be able to, almost like a hand of God, set those values. And so that's something that we're looking to add in the future, is a way that you can kind of do a negative feedback mechanism to drive towards the value that's set by the user. That's something that's a little weird because it's not based on, you know, an actual physiologic event. You're just manipulating the feedback to get the exact value you want. Another thing that it would be really nice is what I call try before you buy graphical user interface. So that's one thing I think is lacking, is a way to show off what we've done. So like I was saying with what BioGears is and what BioGears isn't, it's hard to kind of describe what's going on under the surface and inside the engine if you don't have a really flashy interface that you can play around with, and I can give him all these different acute injuries, and I can start doing interventions for those injuries and kind of see how the different systems are responding. So that's one thing that I think should be added in the future, is something that kind of comes along with BioGears itself. It's really fancy, not, you know, one of these applications by a third-party source. And then something that we realize is people don't necessarily want all the functionality all the time. They might want just a cardiopulmonary model with drugs, and that's all they really care about. But they want to be able to run 10 instances at once because they have a game where they're trying to do triage. And so another place is trying to kind of limit some of the fidelity so that we can run faster and run multiple instances. And then everyone always wants new injuries and new conditions. I mean, we're modeling a whole lot of things. You can see the list of what we're doing online, but it's, you know, never enough. Things like burn is a big one recently, or I don't know, you name it, even more drugs, doing things with overdoses and you think of any area and there's someone who cares about it. But hopefully we've made the model extensible enough and modular enough that you could add your own models for those different things and kind of give back to the community. If you look at the pictures on the right there, so you can kind of see the top one is of us at Syndaver Labs. So that's a synthetic cadaver, which is one of the places that we went to kind of see where they could use BioGears engine. The next one down is of our BioGears conference, which we actually held back last October, and I think it was pretty successful. We had over 100 people for the first time ever for a software user group that, you know, software had only been released for a year, so I think that was really great. You can see there in the middle left our fearless leader, Harvey McGee, our Gore schmoozin. Rodney Matoyer's in the bottom right, showing off a poster that he presented at Modeling Meets Virtual Reality MMVR conference. And in the bottom left, you can kind of see a display that we put up when we went to a test and evaluation event for SOCOM. And now, final little section, I promise, just a little bit about a conclusion. So basically how to use BioGears, just go to the website. There's information on how to download, there's information on how to run it, there's information on how you can integrate it. You know, we've designed it to be as extensible as possible and to have improvements that can be integrated over time, not only by us, but by the entire user base. And basically just let us know any way that we can help. We would also, you know, I want to mention that we'd love to keep working with CPMS as they define a certification process. I think that's something that's definitely lacking. And standardization guidelines would be really nice, because we've gotten questions before of like, well, you know, who says that your models work? And it's like, well, we've documented them, but there's no, you know, real seal of approval that's out there to be able to say, yeah, you know, this is a trusted source. They're doing exactly what they should. And then how can you contribute? So I've mentioned a lot about how we're always looking for the community to use their own applications and let us know what they do. So if you do, just let us know. We have, if you look at the front page, we put all of our collaborators and integrators there, and so we'd love to post you all prominently on there and put a link to whatever website you'd like. Reporting problems is always helpful for us too. We have a list of known issues, but anytime there's other things that we may or may not know about, it's good to know. Posting the forums is always helpful. We are always here to respond to any questions and to help you get going and to answer how do I integrate my model? How do I get this running? I know Aaron, our lead developer, answers a lot of questions about why isn't my Java working? So if you have any of those too, I would first read what other people have posted. We've answered some of those, but if you're still stuck, just let us know. You can always give us a call and send us an email too. Go to that Work With Us page. It's probably the easiest way to find us. And pretty soon we will be moving to a public repository. So we are technically on GitHub now, but we don't have an easy way for people to contribute. So for now, just email us a code, we'll review it, and we can insert it at that point. But otherwise, in the future, we'll be able to use Bitbucket and GitHub in the way that it's intended. As people who have been doing work in this area and doing software development are probably aware. And with that, I'll turn it back over to Joy.
Great, thank you so much, Jeff. That was a great talk. Very interesting to hear about all the ways you're doing validation and how you're getting people interested in BioGears. So we're going to go ahead and open up. I see a bunch of questions that have already been posted on the Q&A panel, and I know Rodney and Aaron have been addressing some of those. If you do want to ask a question, just follow directions, ask it through the Q&A panel, and make sure you ask it of all panelists. So I know Rodney and Aaron have addressed some of these already, but just to bring it to the attention of the whole group, I'm going to repeat some of them verbally so Jeff can address them. So Grace Pang asks, what kind of uncertainty quantification do you perform in your physiology model?
Right, and I'm not sure how they answered this, but that's one place that I think is kind of lacking is we change, we look at all the different actions and we do it in different ways in different ordering, but we don't necessarily do a good job of really looking at, as these different feedbacks get different values, how sensitive they are, basically.
Is that something that people ask you about? And is it a limiting factor where some people say, oh, well, if you don't have that, then we aren't going to be using BioGears?
I don't know if they've kind of given that hard of a stance, but it's definitely a question that does come up quite a bit, and it's something that I think we should definitely look into in the future for sure.
Okay, and so along those lines, I was also curious, what are some of the other concerns that potential customers have brought up aside from that? You've obviously paid a lot of attention to creating a really credible tool, and you're very transparent. What are some of the other issues that they have?
Right. Right now, one of the issues we're really working on is speed. We're only really twice real time, so it's hard to, while you can run it, everything we're doing and how complex the models are, I think it's actually pretty impressive that we're running that fast. But that being said, it's really designed to be run right now on a laptop, whereas users would like to be able to run it in lower level little kind of microchip systems. And so some of those I kind of addressed in that list of known things that can be improved, and figuring out ways to kind of be able to remove some functionality to get that performance increase. That, and then the other major one that we always get asked is overrides. That's one thing that I know is huge in that mannequin training community, is figuring out a way to, if the instructor wants to throw a curveball and wants to change a value, specifically what they want to see how the trainee responds, is being able to do that, but being able to do that in a physiologically correct way, not just displaying a separate value, but seeing the body respond to that.
Okay, thanks. So I think we also have this question from Robert Hubel, which I think someone's in the process of addressing by text, but okay, perhaps you can also address this verbally. So you mentioned that it'd be great to have CPMS or some other independent party provide some kind of seal of approval. Robert wants to know what third-party scientific validation has been done on either the overall engine or the individual models that you've incorporated.
So no one's done, as far as I know, official third-party validation. you know, we have a pretty extensive user base already that's still growing. So they, you know, respond as they find things that are incorrect, but there hasn't been anyone kind of tasked with that, I guess, at this point.
So aside from having a central body like CPMS or some other group do it, would you expect just that as people adopt it, perhaps they will use the engine and then publish results based on it? Is that part of the vision of your third-party scientific validation?
Yeah, I think so. I mean, that's not necessarily, you know, specifically for validation, but it definitely helps validate that what you're doing is correct. If, you know, the more peer-reviewed articles and presentations that are giving using BioGears as the backbone, the more validity I think that it has for sure.
But you think that a more formal validation process is still needed?
Yes, yeah. You know, one thing we've been going through at our office quite a bit lately is what's called CMMI approval, and that's making sure, you know, that you have correct things in place for the processes that you use. And while it's a huge pain, once you get that seal, then everyone, you know, basically agrees, oh, you know, you definitely use practices that are correct for that. And so I think it would be nice for, you know, us to be able to say when they question us of, well, you know, I know you think this is good, and I know you've documented everything and you think you validated it, but who are you to say that it's valid? And so we definitely lean on our subject matter experts to help us with that. But it's always good to have that third-party source to kind of you know, make sure that you're not sweeping things under the rug, whether you really intend to or not.
Mm-hmm. That makes sense. So Harvey McGee had a comment saying that the first annual conference was very successful in his opinion as the Department of Defense. Sorry, my menu jumped there.
No problem.
As the Department of Defense grants officer representative, meaning government oversight guy.
Yeah, well, I appreciate that from Harvey, and he did a fantastic job. He was in charge of putting together a panel with some other government people to talk about some of the programs they're using and how BioGears could be implemented with those. So we always appreciate all of Harvey's help. He's a great Gore.
And then from Satoshi Oda, he asks, can you tell me about a relationship with the Virtual Physiologic Human project?
Yeah, so the Virtual Physiologic Human project, actually Rodney Matoyer, the lead physiologist, and I this fall are going to the conference just in October. And we have a table there, and Rodney's also giving a presentation, and I think there's definitely a lot of synergy kind of between our organizations. We've never really had the opportunity to focus on that relationship in the past, but I'm kind of really hoping that it blossoms in, because I think we could really help each other out. And I actually even have, I was just looking for it, there's a quote that I really liked that they had on their website that kind of, I think, mimics the story that I was trying to get across, that, you know, the virtual physiological human is not the supermodel that will explain all possible aspects of human physiology or pathology. It is a way to share observations, to derive predictive hypotheses from them, and to integrate them into a constantly improving understanding of human physiology and pathophysiology. So it's kind of it's not the be-all, end-all, but it's a way that people can then, you know, add to it, basically. So we're really excited about that possible relationship.
Yeah, that'll be exciting to see how the two of you can be synergistic.
Mm-hmm.
Do we have any other questions? So I'll throw one more in there while we're waiting to see if we have any last questions here. So I was curious because in your talk you said that clinicians don't care about what goes on under the hood as long as the results are correct. So to me it sounds like, you know, a systems approach might actually be sufficient for them. And so I'm curious, given that criteria, why would they choose to go with BioGears?
Yeah, I think, so I'm not sure if there's a systems approach at that level that we'll be able to combine all the different things that a clinician kind of wants to do. Because if you say I have a patient with specific parameters who has a condition like lobar pneumonia, and then I want to have a hemorrhage and give them drugs and, do all the patient variability that goes along with that. If you don't do it with a kind of mechanistic approach, with each kind of step in that process validated, it starts getting to be a huge headache for all those different combinations and permutations if you just try to do curve fitting or more state-based type modeling.
Great. That clarifies why they would want to go with you guys. So last question from Sam Nemoitin here. He says, do you support arbitrary chemical reactions? And he's saying he guesses that there's no diffusion, simulated, or subcellular level.
We do model diffusion, so we do alveolar diffusion of O2 and CO2 getting between the respiratory and cardiovascular system. It just uses a very simple diffusion equation based on the partial pressures on either side of that boundary. We also do it, and we're updating that model actually today as we speak on the tissue side of things, going from the vascular to the extravascular and extracellular side. And then we are working on inhalation models of different substances where you could use it for things like sarin or cyanide. You could use the same kind of modeling approach. We also have a model for an inhaler that uses albuterol. And so in that way, the inhaler basically just modifies the parameters of the volume fractions of what the makeup of the air going into the lung is. It has a very, very, very simple model for deposition, and then it does the same kind of alveolar exchange based on those physicochemical properties of albuterol itself. So we are working towards that. That's one of our requirements, and we're, I would say, about 80% of the way there.
Great. Well, thank you all for the great questions, and thank you, Jeff, for taking the time to present. Can you go on to the next slide?
Sure.
So to learn more about CPMesh, you can visit our website here. We also encourage you to continue this discussion about BioGears on their forum, and also to continue the discussion about translating models and simulations to the clinic on our forum. Please take a few moments to fill out the survey that's going to appear at the end in a pop-up window once you close out the webinar. This will help us improve our webinars and choose upcoming topics. So thank you all for participating, and we hope to see you at future webinars. Thanks again, Jeff.
Thank you.